Tell me about a time you designed a scalable system. Introduction. This is an important behavioral and system design interview question for software developers, senior developers, backend developers, full-stack developers, team leads, and engineering managers. Interviewers ask this question to understand how you design systems for growth, how you handle high traffic, how you avoid bottlenecks, how you use caching, queues, and databases, how you design for reliability, how you think about trade-offs, how you validate scalability, how you monitor production systems. This question is especially important for Java developers, backend developers, full-stack developers, senior software developers, cloud developers, team leads, system design interviews. The best way to answer this question is by using the STAR method. STAR means S, situation. Explain the background. T, task. Explain your responsibility. A, action. Explain what you personally did. R, result. Explain the final outcome. A good interview answer usually spends 10% situation, 10% task, 60% action, 20% result. The most important part is the action section, because interviewers want to understand your design decisions, trade-offs, and scalability thinking. Question. Tell me about a time you designed a scalable system. Example 1. Designing a scalable REST API system. In one project, we were building a new customer-facing feature that was expected to receive high traffic during peak business hours. The initial implementation idea was simple, but we knew the system had to handle future growth without slowing down the application. Task. I was responsible for designing the backend API flow so it could scale with increasing traffic while remaining reliable and maintainable. Action. I started by identifying the expected usage patterns and possible bottlenecks. I reviewed. Check. Expected request volume, peak traffic windows, database read-write patterns, response time expectations, external service dependencies, failure scenarios, monitoring requirements. Then I designed the API using a layered architecture with clear separation between controller, service, repository, and integration layers. To improve scalability, I added pagination for large result sets and avoided returning unnecessary data in the response. I also designed database queries carefully by using indexed filter columns and selecting only required fields. For frequently requested reference data, I added caching with proper expiration rules. I also made sure the API was stateless so it could scale horizontally behind a load balancer. For reliability, I added structured logging, correlation IDs, error handling, and monitoring dashboards. Result. The API handled peak traffic successfully after release. Response time stayed within the expected range, and database load remained stable. Because the API was stateless and well-monitored, the system could be scaled horizontally when traffic increased. Why this answer works? This answer is strong because it shows: check, scalable API design; check, stateless architecture; check, database optimization; check, pagination; check, caching; check, production readiness. Example 2. Designing an event-driven system using Kafka situation. In one backend system, a user action triggered multiple downstream updates. Initially, the application handled everything synchronously, which made the user requests slow and tightly coupled to downstream services. Task. I was responsible for redesigning the flow so the system could handle more traffic and reduce dependency on downstream service availability. Action. I started by mapping the full request flow. I identified which operations were required immediately and which operations could happen asynchronously. I found that several downstream updates did not need to block the user response. So I proposed an event-driven design using Kafka. The new design was user action dash main API validates and saves core data. API publishes event to Kafka. Kafka consumers process downstream updates asynchronously. I designed the event payload with a unique event ID, timestamp, event type, and business identifiers. To make the system reliable, I added idempotent consumer logic, retry handling, dead letter queue, event status tracking, monitoring for consumer lag, alerting for failed messages, audit logging. I also worked with QA to test successful processing, retries, duplicate messages, invalid messages, and downstream failures. Result: the user-facing API became faster because it no longer waited for all downstream systems. The system handled higher traffic more reliably. Downstream failures no longer blocked the main user request, and failed events could be retried or reviewed safely. Why this answer works? This answer is strong for backend and senior developer interviews because it shows event-driven architecture, Kafka design, asynchronous processing, idempotency, retry handling, dead letter queue, scalability, and reliability. Example 3. Designing a scalable search feature situation. In one application, users needed to search a large number of records using different filters. The existing search approach worked for small data, but as the data grew, search response time became slow. Task: I was responsible for redesigning the search feature so it could support larger datasets and still return results quickly. Action: I started by analyzing the existing search behavior. I reviewed common search filters, sort patterns, result size, database query execution plans, indexes, API response size, user expectations. I found that the search query was scanning too many records and returning large responses. To improve scalability, I redesigned the search API to support pagination and filtering. I also worked with the database team to add indexes on frequently filtered and sorted columns. I changed the backend logic to apply filters earlier in the query and return only required fields. For common filter values, I added caching. I also introduced a maximum page size to prevent large unbounded requests. For future growth, I documented when we should consider a dedicated search engine such as Elasticsearch or OpenSearch. Result: search response time improved significantly. The database load decreased because queries became more targeted. The feature became more scalable because large result sets were paginated instead of returned all at once. Why this answer works? This answer is good because it shows search scalability, indexing, pagination, query optimization, response size control, future architecture thinking. Example 4. Designing a scalable batch processing system situation. Our application had a nightly batch process that handled thousands of records. As data volume increased, the job started taking too long and delayed downstream reporting systems. Task: I was responsible for redesigning the batch process so it could handle larger data volume efficiently and reliably. Action: I started by reviewing the current batch job flow. I analyzed. Check record count, processing time per step, database calls, file reading logic, error handling, restartability, downstream dependencies. I found that the job processed records one by one and made repeated database calls inside a loop. To improve scalability, I redesigned the job using chunk-based processing. I added check configurable chunk size, batch inserts and updates, cached lookup data, step-level logging, record-level validation, skip logic for invalid records, restartability support, clear error reporting. I also tested the job with production-like data volume and adjusted chunk size based on performance results. Result: the batch job execution time was reduced from several hours to a much shorter processing window. The job became more reliable because invalid records no longer stopped the entire process. Downstream reports were generated earlier and support effort decreased. Why this answer works? This answer is strong because it shows check batch scalability, chunk processing, check database optimization, check restartability, check error handling, production data volume testing. Example 5. Designing a scalable file upload system situation. In one application, users needed to upload documents and images. The original design stored files directly through the application server, which created performance and storage concerns as usage increased. Task: I was responsible for designing a more scalable file upload flow that could handle larger files and higher upload volume. Action. I started by identifying the main bottlenecks. The application server should not become the storage layer.
So I proposed separating file storage from application processing.
The scalable design was: user uploads file, backend validates metadata and permissions. File is stored in object storage. Database stores file metadata. Async process handles scanning or processing. User receives upload status. To improve scalability and reliability, I designed file size validation, file type validation, object storage integration, metadata storage in database, asynchronous processing for heavy work, retry handling, upload status tracking, secure access control, monitoring for failed uploads. I also avoided storing large files in the database and kept the application server stateless. Result: the upload system became more scalable and reliable. The application server was no longer overloaded by file storage. The system could handle larger files and higher upload volume with better monitoring and error handling. Why this answer works? This answer is strong because it shows scalable file architecture, object storage design, metadata separation, async processing, stateless backend, security awareness. Example 6. Designing a scalable notification system. In one project, the application needed to send notifications to users for important account events. The initial idea was to send notifications directly inside the main transaction, but that would slow down the user-facing flow. Task. I was responsible for designing a scalable notification system that would not affect the main application response time. Action. I proposed moving notification sending to an asynchronous flow. The design was: business event occurs. Application saves transaction. Notification event is published. Notification service processes event. Email, SMS, or in-app notification is sent. Status is tracked. I designed the notification system with message queue or Kafka topic, retry handling, dead letter queue, notification status table, template management, user preference checks, rate limiting, item potency, monitoring and alerting. This allowed the main business transaction to complete quickly, while notifications were processed separately. I also made sure failed notifications could be retried without duplicating messages. Result: the notification flow became scalable and reliable. User-facing transactions were not slowed down by email or SMS processing. Failed notifications could be tracked and retried safely. Why this answer works? This answer is good because it shows asynchronous design, decoupling, queue-based processing, retry handling, item potency, user experience improvement. Example 7. Designing a scalable multi-tenant system situation. In one SaaS-style application, multiple organizations needed to use the same platform while keeping their data separated. The system had to support more customers over time without creating a separate deployment for every organization. Task. I was responsible for contributing to the back-end design for tenant-aware data access and scalable onboarding of new organizations. Action. I started by reviewing how users, organizations, roles, and permissions were modeled. Then I designed the back-end flow so every request included tenant context from the authenticated user. The service layer and database queries used tenant ID filtering to ensure users accessed only their organization's data. I also designed common tenant-aware patterns for check authentication, check authorization, check database filtering, check API request validation, check audit logging, check onboarding new tenants, check role-based access, check monitoring by tenant. To support scalability, we avoided creating separate code paths for each tenant. Instead, we used shared services with tenant isolation at the data and permission level. I also added tests to verify that users from one tenant could not access another tenant's data. Result: the system supported multiple organizations using the same application. New tenants could be onboarded more easily. The tenant-aware design improved scalability while maintaining data security and separation. Why this answer works? This answer is strong for SaaS and backend interviews because it shows, quote, multi-tenant architecture, quote, tenant isolation, quote, security, quote, scalable onboarding, quote, shared services, quote, authorization design. Example 8. Designing a scalable analytics dashboard situation. In one application, business users needed a dashboard showing summary metrics from large transaction data. The original approach calculated metrics directly from raw transaction tables every time users opened the dashboard. As data volume increased, the dashboard became slow. Task. I was responsible for designing a more scalable approach to load dashboard metrics quickly. Action. I started by analyzing which metrics were needed and how often they changed. I found that users did not need every metric to be calculated in real time. Some metrics could be pre-computed periodically. So I proposed a design using summary tables. The flow was raw transactions, scheduled job or event processor calculates summaries. Summary table stores aggregated metrics. Dashboard API reads from summary table. Front-end displays results quickly. I also added check, date-based aggregation, tenant or user filtering, incremental updates, indexes on summary tables, cache for frequently viewed metrics, monitoring for summary job failures, fallback behavior if summary data was delayed. I worked with the business team to confirm acceptable data freshness. The dashboard loaded much faster because it no longer calculated everything from raw transaction tables on every request. Database load decreased. Business users could access metrics quickly, and the system became ready to handle larger transaction volume. Why this answer works? This answer is strong because it shows CUC, analytics scalability, pre-computation, summary tables, data freshness trade-off, database load reduction, business collaboration, best short answer version. If you need a short interview answer, you can say, in one project, we had a user action that triggered multiple downstream updates. Initially, everything was handled synchronously, which made the API slow and tightly coupled to downstream services. I was responsible for helping redesign the flow so it could scale better and remain reliable as traffic increased. I mapped the full request flow and identified which operations were required immediately and which could happen later. I found that several downstream updates did not need to block the user response. I proposed an event-driven design using Kafka. The main API validated and saved the core data, then published an event. Consumers processed downstream updates asynchronously. I also added idempotency, retry handling, dead letter queue support, monitoring for consumer lag, and audit logging. As a result, the user-facing API became faster and more reliable. Downstream failures no longer blocked the main request, and the system could handle higher traffic more safely. Common mistakes to avoid. 1. Saying only I used microservices. Bad answer. I designed a scalable system using microservices. Better answer. Explain why microservices were needed, what bottleneck they solved, and what trade-offs you managed. 2. Ignoring data bottlenecks. Bad answer. We scaled the application servers. Better answer. Also explain database indexing, query optimization, caching, pagination, and data access patterns. 3. No trade-off discussion. Bad answer. I used Kafka because it is scalable. Better answer. I used Kafka because downstream processing did not need to block the user request, but I also designed retries, idempotency, and monitoring to handle added complexity. 4. No reliability design. Bad answer. The system could handle more traffic. Better answer. Explain retry handling, dead letter queue, error handling, monitoring, alerts, and fallback behavior. 5. No measurable result. Bad answer. The system became scalable. Better answer. API response time improved, database load decreased, and the system handled peak traffic without failures. Best practices for answering this question. CAP. Use the STAR method. Explain the scalability problem clearly. Mention expected traffic or growth. Identify bottlenecks. Explain design choices. Discuss trade-offs. Include caching, queues, database, and monitoring where relevant. Explain reliability and failure handling. Mention testing with production-like data, and with measurable impact. What interviewers are looking for. Interviewers want to see whether you can check, design for growth, identify bottlenecks, build stateless services, use caching correctly, use asynchronous processing, design reliable message processing, optimize database access, plan for monitoring and alerts, think about failure scenarios, explain trade-offs clearly. For senior roles, they also want to see check, architecture ownership, scalability trade-offs, operational readiness, cost awareness, security awareness, long-term maintainability, mentoring or team-level design guidance. Strong words to use in your answer. You can use words like CUC, designed, scaled, decoupled, optimized, partitioned, cached, paginated, monitored, load-tested, validated, improved throughput, reduced latency, improved reliability. Example: I redesigned the synchronous flow into an event-driven architecture, decoupled downstream processing, added idempotency and retries, validated the design with load testing, and monitored consumer lag after release. Scalability areas you can mention. Depending on your experience, you can talk about Codalao, stateless REST APIs, horizontal scaling, load balancers, database indexing, query optimization, caching with Redis, pagination, Kafka or message queues, asynchronous processing, batch processing, object storage, multi-tenancy, rate limiting, circuit breaker, retry handling, dead letter queue, monitoring and alerting, check. Summary tables, check. Search optimization, check. API response size reduction. Final summary. Tell me about a time you designed a scalable system is an important interview question for software developers and senior engineers. The best answer should include what scalability problem existed, why the existing design was not enough, your responsibility, how you identified bottlenecks, what design choices you made, what trade-offs you considered, how you handled failures, how you validated the design, what result you achieved. Good examples include Scalable REST API design, Kafka event-driven system, scalable search feature, scalable batch processing, scalable file upload system, scalable notification system, scalable analytics dashboard. The strongest answers show architecture thinking, practical trade-offs, reliability, monitoring, and measurable impact.